Hey guys, welcome to the video. I hope you remember that in the first video of the series on the VSEPR theory, we talked about how important is molecular geometry, and we talked about how to find this out, how to find the electronic geometry and the molecular geometry, right? We talked about where we did use several electron pairs. We started with if there are two electron pairs, which is 2 bonding plus 0 lone pairs, then we have linear structure. Then we said if we have 3 electron pairs, electron groups, then that could be 3 plus 0 or 2 plus 1. In both cases, while the electronic geometry would be, in this our case, trigonal planar, we understood the rule that if there is no electron pair, then molecular geometry is going to be same as electronic geometry. But because we have an electron pair here, we understood that this is going to be a little bit bent. Now in today's class, we are going to start or talk about where we have 4 or 5 electron groups to discuss with. I hope you remember the problems that we discussed in the last class. We will also be looking at 4 and 6 electron groups involved, right? So we'll be talking about that in today's video. Let's tackle the molecule CH4. Now this is pretty easy. Carbon valency, we know the atomic number is 6 and hence it's 2, 4 valence electrons. Hydrogen, atomic number 1, valence electrons 1. So first step is pretty simple. Let's write 4 valence electrons of carbon, write 4 valence electrons of hydrogen, and there we have 4 4 electron groups, right? Count the number of electron groups. We have 4, right? Now arrange. Now 4, what the best thing to arrange them is perhaps in a tetrahedral. So what is the electronic geometry that you are going to get? That is tetrahedral. Now the next problem comes is to determine the arrangement of bonded atoms. Now we read about in the last video that since there are no lone pairs, hence the electronic geometry is going to be same as molecular geometry. Hence it would be tetrahedral. Now let's talk about bond angles, and that would be 109.5 degrees. That's okay. Talking about polarity, well, we can expect a little bit of game here again. Now we know for sure that there is difference of electronegativities here, right? Carbon is around 2.5, hydrogen is around 2.1, but the thing is the bonds are placed in such a geometry that if you see, they cancel out, right? And hence net dipole, if you want to mention, that equals to be 0. Let's look at the complication NH3. So nitrogen is 7, 2, 5, and hydrogen, well, it's poor hydrogen, just 1. So nitrogen, 2 lone pair of electrons, and obviously we have 3, right? So H, each with 1 valence electron. Now you want to find out the number of electron groups, 4, right? So electronic geometry is again going to be tetrahedral. That's not a biggie. But the problem is, what about this lone pair? Now we read in the last video, and I hope you remember that. If you don't, you can go and check it out right now, that when there is a lone pair, what it is going to do is it's going to push these electron groups a tad closer, right? So what we can assume is that this is going to be, we attach 3H, and this angle was supposed to be 109, but now it's not 109, instead it is 107.3 degrees. Now we know why does this happen. Now let's talk about polarity, because an important part of molecular geometry is polarity. Now we know that this nitrogen is more electronegative, right? Now I'm not going to write the electronegativity here, because it's sort of something that you can get from the periodic table. And then again the electron cloud is here. So what you see is it's very polar molecule because of its geometry. Now you must name this shape. So this shape is called trigonal pyramidal. Now remember, we are naming this only for the molecule. The electronic geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. Okay, now let's talk about something more interesting. So we have two bond pair and two lone pair electrons. So if you are watching this video right now, I want you to follow the steps that we outlined and do it here if you haven't already done. So right now you can hit a pause and you can do it. And I would be discussing the result after 10 seconds. So here's your pause. Okay, so I'm hoping that you have already done it. So now I'm resuming. I did not actually pause for 10 seconds, but you can clearly see that oxygen is going to be double bonded here, and it is going to have two lone pair electrons, right? Two lone pairs. So this is going to push the angles further, and hence you have actually, instead of 109 point something, you have 104.5 degrees. So you see that the angles reduces further, right? Because we have two lone pair electrons. Because of the shape of these angles, the molecular geometry here is going to be bent, or simply you can call it angular. The most difficult problems involving the VSEPR or theory are the ones involving the 5 electron pairs. So I hope you remember that we signed ourselves a few problems. So if you haven't done them, again, this is the time when you hit a pause button and you can practice for all 5 molecules that are written right here. For your help, what I have done is I have written already the valence shell electronic configuration for those things. Now remember, these are only representing the valence shells. Now you have to think, how should the electronic configuration change if you are to achieve these things, and what are the steps? It's already outlined here. So hit the pause button and walk it through, and then we'll discuss it in this video right here itself. Okay, so now I'm imagining you have done your work, and let's talk about these. Now, the first thing is write the Lewis formula. Now, before going ahead, what I'm going to do is I am going to talk about the 5 electron pairs. Now, what's the best way to keep all the electron pairs away from each other? Now, you can imagine that would be trigonal. That means electron groups at the apex of each, and then bipyramidal. Bipyramidal means these angles are going to be 90 degrees, whereas these angles between these should be 120 degrees, right? So this is how the electronic geometry of all these compounds should be. But obviously you have to take into account the lone pairs. So now let us work each of them one by one, and let's see where it goes. Okay. Okay, let's work PCl5. Now, phosphorus, P has to bond with 5 chlorine atoms. Now, the first step, as we do for all the other ways, is you have to write the Lewis formula. But for that, you have to also justify how does phosphorus get to have 5 bonds. Now, if you look at here, the configuration is 3s to 3p3. So S is completely filled, where P can take 3 electrons in its 3 orbitals, right? One is already filled. So how does it take 5? Now that happens because, remember, the number of spg, the orbitals, can be the same as this number, right? This quantum number. So actually they do have 3D, right? Now the electron can be promoted to 3D, Why do we do this promotion? Because then we have a half-filled orbital, and a half-filled orbital grants some more stability. So right now we have 3s1, 3p3, 3d1. So now you see one electron can be added here, 3 added here, 1 added here. That means you have a valency of 5. So let's put these 5 electrons right there. Chlorine, it's very easy. Chlorine is 17, 287. So I'm just gonna write the valence electrons here and not the lone pairs, because kind of they are not very important here, right? So as you can see, we have 5 electron groups, no lone pairs. So here the structure is that going to be trigonal bipyramidal without any problem. But the problem comes when you go a little bit away, that is SF4. Again, now guys, it's very important, or I would say it's good for practice if you are always doing the electronic configuration. Why? Because it just strengthens your understanding. So S is again 16, right? So 2, 8, 6. That means the third shell 3s2 and 3p4. And again, there's just 2 that it can take, but you can see the formula F4. That means we need more orbitals, and very easily you can take that the 3p has 4 electrons. Now if you promote one of this fourth electron to 3d1, you have a half filled orbital that gives you some sort of extra stability. So you can add 3 electrons here, 1 electron here, that gives you the valency of 4, right? So center you have S. Okay, so you have there, and then what you do is you put on F, you put on F, you put on F, and you put on F. And here what you have is your lone pair of electrons. Now this gives a little bit of seesaw appearance. I hope you can imagine this. Why? Because you know that as long as there is a lone pair of electron, it is going to push the other bonds closer to each other. Now, one thing that you should imagine is the repulsion between the electron groups. So generally the lone pair repulsion is the greatest. Then you have lone pair base pair repulsion, and the least strong is the bond pair repulsion, right? So here we have repulsions between the lone pair and bond pair, right? That is what is pushing them into that particular geometry. Now, the other molecules that are written here, that is PCl5 and XeF4, are going to increasingly go out of the trigonal bipyramidal model, and in case of PCl5, what you'll find is that the shape is that of a T. So it's T-shaped. Similarly, in case of XeF2s and fluoride, you'll find it is of linear shape. So working through these problems will help you get better at it. Now, if you hope to get better, also try for 6 electron pairs. If you haven't already done this, again, I will be pausing for a second here. So you can stop the video right here, go back, practice these problems, and come back to the video. Here is the pause. Okay, so I hope you have practiced them, and now we are going to talk about this. Now, again, for your help, what I've done is I have already written the valence configurations right here for the elements, right? Now, you have to first write the Lewis formula for each of these, count the electron groups, arrange the electron pairs according to VSEPR theory. Now, straight away, let's talk about the electron geometry first of all. Now, you know, we are talking about 6 electron pairs, and what's the best way to sort of, you know, keep them out? So that comes out to be square, right? So it's octahedral. The perfect way to call it is octahedral. So you have a you know, the electron groups, 4 electron groups occupy the corners of the square, and then you have 1 electron group on the top, and one electron group on the bottom. So what are the angles between them? That is 90 degrees. And what is the angle here? That's again 90 degrees, right? So you should remember this is what the electron geometry is going to be. But again, because we have taken the lone pairs when present, they will influence this to a lot more extent. Let's do one example at least, and I'll leave the remaining for you to practice on your own. So SF6, now again, remember we need 6 bonds, right? Now if you see 3s2, 3p4, you see you do not have the scope for 6. So that means you have to promote this, right? 3s2, 3p3, if you do, then you'll have 3d1. Again, not so satisfactory. So what we can do is instead promote this little guy there as well, right? So let's do that. Okay, so we have 3s1, 3p3, 3d2, right? So what you can see 1 plus 3 plus 2, that is equals the valency of 6, right? So that's pretty simple. So you have S at the center, you have F at the four corners of a square, you have one F popping out, one F popping in, and that's the symmetry, that's the geometry, even the molecular geometry, that is octahedral. Now this is only because you do not have any lone pairs, right? The moment you have lone pairs inside, like in case of IF6, what will happen is things are going to be changed. So in case of IF6, the lone pair are going to bend things a little bit, and you have square pyramidal. In case of XeF4, you have square planar. Why do you have that? Because in case of XeF4, what do you have is lone pairs. So all the fluorine occupy the four corners of the square, and you have lone pairs on top and the bottom of the plane, right? So that is why square planar, they all come as a perfect square. So what you can see is the molecular geometry. How is it determined? Now I want you to remember where we started in the very first part of the video. We said that to study molecular shapes, we will be first using the theory VSEPR, which only talks about the location of electrons and atoms, right? But then we say this does not talk about the process of bonding, right? And for this, we said we'll be covering another theory called the valence bond theory. Now, several people and educators want or take this hand in hand, but for a clarity of concept, I have kept them separate from each other, which is an approach followed by the other fraction of educators. So once you finish or sort of master this concept, it's time that you skip to or jump to the next in the series where we discuss the valence bond theory. Now, it's very important that you watch the whole sequence beforehand, because the valence bond theory requires you to know the VSEPR, but without VSEPR, you won't be able to deduce the information that you want for the valence bond theory.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.